Okay, welcome to this session, and in this session we will do some data exploration. We call that in data science, we call it exploratory data. You have installed Anaconda, log into your account, and you will have this. Each student has a folder where I put all your data there, but before we go there, we will do some other exploratory data analysis using Essex and Forrest data. Population of soybean. So a population of soybean, Essex by Forrest, that's where E by F comes, in 2000. So if I open this, so that's some exploratory data analysis using Essex by Forrest Recombinant Inbred Line population 2010 data. So in this data, it's a data frame like Excel here. So where you have individuals, I have 94 rails from individual 1 to 94, and I have some isoflavones there. Their content in the seeds. So you have dadzine, genistein, glycetane, and total isoflavones by adding those three. So this is in microgram per gram of seed, just to give you an idea. So first, what you do in Python when you get here, you will import the libraries that you will use. So we import pandas, that's what allows you to do the data frames like here. We use NumPy. NumPy is actually to do some statistics and etc. We will get to that. And Matplotlib is to do graphs. Okay, and Seaborn also for graph. So basically run this. Okay, so it's running now in the background. Then here, this cell, you read your data. PD, that's panda, okay. Read CSV, you get your data as CSV, so I put there E by F 2010 isoflavone phenotype. I have it here, so E by F 2010 isoflavone phenotype in CSV format. So you have to have your data in the same folder in order to be able to read it. That run, we run this second one here, it's run. Then head will give you an idea. If everything runs, you can see your data here. If you did DF, that's what we call your data. It's a data frame. You can call it whatever you want. But DF we call it, then you do that head will give you the first 5 rows. If you do 10 here or 15 or whatever, it will give you 10, and Python goes from 0, so 0 to 9, that's 10. So I have 10, but of course I have 94. If I put 94 here, I will have everything. So that's just you explore your data there. Then this code will give you a summary of these dadzine, genistein, glycetane, and total isoflavone with their summary. When you do describe will give you a summary, and this will print this. Okay, so for each column, Python gives you, of course, the count is 94. We have 94 reels, as I said. Then for each numerical column, you might have some non-numerical, we will get to that, but here everything is numerical. It gives you the mean dadzine in your population. It's 1306.82 microgram per gram. Will give you the standard deviation, the minimum and the maximum, then the 25th, 50th, and the 75th quartile for each. So that's a nice, you can put this as a data frame or a table and present it. Then we will do some graphs here. This code allow you to do a graph of each of these within the individual, how it is distributed. So this is the frequency distribution of and density curve here. For dadzine, this is genistein, glycetane, and total isoflavone. Box plots of these genistein, etc. This is a box plot for each of these. We see that in this population here, of course, total isoflavone is high, but the other three dedzine is high in the population, followed by genistein and glycetane. Then we can do a correlation between these isoflavones in the population, and you can see here, if you take genistein, you see it's highly correlated, 0.7. You see high correlation in the red here, close to 1, and the low non-correlation towards 0. Genistein, if you say dedzine is highly correlated with genistein, and of course with total isoflavone. Genistein, highly correlated with total isoflavone and with dedzine, etc. So that's a nice heat map showing you the correlation. You can do pair plot, scatter plot, genistein, dedzine, genistein all the way. And again here, the dedzine, here the correlation is correlated with genistein, okay? Here not very much, but again here with total, it's nicely correlated. When dedzine increases, total isoflavone increases. That's a linear regression. Here not very much, but here is also a highly correlated. You see total isoflavone with dedzine, genistein with total. Here not too much. So that's a very good graph to show you the correlation. You can do violin plot also. This gives you running this code. Here you see the mean for dedzine is about 1250 in the population. In genistein is about 1000 or 980. Here you have glycetane about 200 microgram per gram. Total isoflavones about 2500 or very close to it. So heat map, that's the same thing there with the different colors showing you correlation among these traits. You can do this pairwise comparison. It's not very good because you have individuals, lots of individuals here. But here it's good to show you some clustering if you want, or grouping. This also could be a little bit useful, called cumulative distribution function. Then the PCA is another. All these are concepts we will cover later on. Clustering, this is a population of soybean, 94 reals or individuals. You see here already that we have 3 clusters, and you have the clusters 0, 1, and 2. If you look at dedzine, for example, you will see that cluster 0 has high dedzine, cluster 2 medium, and cluster 1 low dedzine. Here the scatter plot with regression line. So we already talked about that earlier, but here genistein and dedzine, you have a very good line correlation there. Here not so much, not a very good correlation, but total with dedzine is highly correlated. And sometimes you want to find some outliers in your population, and here individual 52 is an outlier. It has a high dedzine, high genistein, high glycetane, and total. Therefore, you may need to delete these outliers from your data.